Welcome back. In the previous video, we discussed Verilog data types, with special emphasis on the difference between nets and variables. We saw that choosing between wire and reg is not a syntax decision, it is a hardware decision. In this video, we will extend that discussion and learn how Verilog allows us to design scalable and reusable hardware using vectors, arrays, parameters, and constants. Real digital systems rarely operate on single-bit signals. We deal with buses, registers, memories, and configurable designs. Vectors and arrays allow us to model multibit and memory-like structures. Parameters and constants allow us to write designs that are flexible, readable, and reusable. These features help us move from toy examples to real FPGA systems. Let us begin with vector data types. A vector is simply a multibit signal. Instead of a single wire or register, a vector represents a group of bits. Vectors are used to represent buses, counters, addresses, and data paths. In Verilog, a vector is declared by specifying a range of bits. For example, an 8-bit vector represents 8 individual bits that are treated as a single signal. Important clarification. A vector can be declared as a net or as a variable. That means we can have multibit wires or multibit registers. In hardware, a vector corresponds to multiple parallel wires or storage elements. One important aspect of vectors is bit ordering. Verilog allows both ascending and descending ranges. However, by convention, we usually write the most significant bit on the left and the least significant bit on the right. Consistent bit ordering is critical for readability and correctness. Confusion in bit indexing often leads to subtle design errors. Now let us move to array data types. While vectors represent a group of bits, arrays represent a collection of elements. Each element of an array can itself be a vector. Arrays are commonly used to model memory-like structures. Register files, ROMs, RAMs, and lookup tables are naturally represented using arrays. In Verilog, we can have one-dimensional or multi-dimensional arrays. A very common and useful case is a two-dimensional array, where each entry is a multibit word. In hardware, such an array corresponds to a bank of registers or memory cells. How an array is synthesized depends on size and access pattern. Small arrays may become registers, while larger arrays may infer block RAMs. Next, we discuss parameters. A parameter is a symbolic constant used to define configurable values in a design. Parameters allow us to avoid hard-coding numbers throughout the code. Instead of rewriting the design for different widths or sizes, we can change a single parameter. Bus width, counter size, memory depth, and timing values are often defined using parameters. Parameters are evaluated at compile time. They do not consume hardware resources directly. Well-chosen parameters make designs scalable, reusable, and maintainable. Constants and local param. Constants represent fixed values used within a design. In Verilog, constants are often defined using parameters. Sometimes, we want a constant that cannot be overridden from outside a module. For this purpose, we use a local parameter. Local parameters protect internal design assumptions. They improve robustness and prevent accidental misuse. Let us step back and see the bigger picture. Vectors help us handle multibit data. Arrays help us model collections and memory structures. Parameters and constants help us write flexible and readable designs. Together, these features allow us to write Verilog code that maps cleanly to real hardware. They are essential for professional quality FPGA design. Common beginner mistakes. Some common mistakes include using single-bit signals where vectors are required, hard-coding numbers instead of using parameters, confusing vectors with arrays, ignoring bit ordering and indexing discipline. Advice: always visualize the hardware structure behind your declarations. To summarize this video, vectors represent multibit signals. Arrays represent collections and memory-like structures. and parameters and constants enable scalable design. These concepts are fundamental for building real FPGA systems. In the next video, we will start writing structural and gate-level Verilog code, applying everything we have learned so far. Please review today's concepts carefully. They will be used extensively in upcoming examples. Thank you.